All right, well, thank you so much for that kind introduction, and thank you everyone for making the time to be here today. There's a lot going on at Stellafane, there's a lot of places to be, and you chose to be here, and I really appreciate that. So just a couple of quick bits. As was mentioned, I work at the Space Telescope Science Institute. I'm obliged to say that everything you'll see today, views are my own, I don't speak for them. In addition, all of the resources that you're going to see today, everything that I show, at the very end there will be a QR code that will take you to a link that has all of the resources, all of the web pages, everything that I'm going to show, so you don't have to try to, hastily scratch anything down. And if you don't have enough phone service to get to that QR code, you can take a card up here. I'll be happy to email it to you. In addition, I just want to mention that once we're all done here, I have a couple of posters that are free giveaway here, courtesy of Space Telescope, with some really beautiful Hubble images on them. There's about 100 posters up there. I think we have just enough, so please feel free at the end to come up and take one and take it home and hang it on your wall. And so finally, before we dive in, I just want to give a really big thank you to Stellafane. To everyone here, all the ST members who put Stellafane on. It is a tremendous amount of work to pull a convention off. The amount of work that goes in before the convention, during and after, and the planning throughout the year is monumental. And so I really appreciate the opportunity to take some of that time. So with that, the game plan. If I can convince you of nothing else today, it's that everyone can contribute to meaningful astronomical research. And I kind of want to hit this in two parts. So the first is I want to just share briefly my journey and some tips about pursuing a career in astronomy. If you're a student or if you know a student who's interested in a career in astronomy, here's a couple of useful tidbits I've found along the way. Then I want to highlight the really critical role that amateur astronomers play in professional amateur collaboration, or pro-am collaboration. And finally, give you some resources to actually go ahead and start diving into research if that's something that you're interested in doing. So I had a very simple beginning, like many folks in telescope making. I dug back, and this was the absolute first picture I could possibly find. I'm pretty sure it was taken with probably one of the first digital cameras too. And this is my optical lab in our basement. So when I was in 6th grade, I was getting into astronomy, I was joining my local observatory, and I found online that people were building their own telescopes. I found James Lurch's website, grinding and polishing binoscope mirrors, and I thought there's no way you can do that. And it just seemed so interesting. So I went to my parents and I said, I need you to order me a 6-inch mirror grinding grit kit. And they said, okay, what is that? So I explained it, they ordered it, and I built this little optical lab in my basement. I had a extremely high precision seated optical grinding bench, also known as a bunch of wood that I hacked together with some nails. I had a extremely impressive gravity-fed low volume water washing system, also known as a bucket, and a small shelf. And that's what I got started with my 6-inch mirror. As time went on, my equipment grew and my digital camera got a little bit better. So I started building an optical bench, basically just sitting on a couple of sawhorses and a bunch of 2x4s, which I just basically plopped everything down on. But the key is it worked. And that's what I love about amateur telescope making. You can build almost anything you can think of. If you want a specific type of instrument and it's not commercially available, then too bad, you don't have it, right? But no, you can build it. So if you want a really super long planet-killing telescope, you want a really fast, deep, ultra-wide field Dobsonian, whatever it is, you can build it, and it's not available anywhere else. The second piece that really drew me in was the precision and the accuracy, right? With your own hands, you can form an optical surface that is accurate to within millionths of an inch across a huge surface. And that is just incredibly impressive that you can do that with your own hands and some fairly simple optical tests that you can build using example plans that are available on the Stellafane website, and as we're seeing in the optical demos just across the hallway here. So around this time, I started getting more involved in the observatory. I met my good friend Matthew Fuchs, who got me hooked on Stellafane. I ran into him at the observatory one night, and he had a home-built telescope, and I was just about starting to polish my mirror, and I had absolutely no clue what I was doing. And so I ran over there, and I asked him about his scope. He told me all about it. He gave me some tips for making a pitch lap and polishing my mirror. And he said, hey, do you want to go to Stellafane? And I said, what's that? And he described it to me, and I said, absolutely, that sounds awesome. So I came to my first Stellafane more than 20 years ago. I hit my first swap tables then, so I went from working on one mirror to working on more mirrors than I could count. basically as much glass as I could physically load into their car, because I didn't have a driver's license yet, I brought back with me. So this was just after my first Stellafane. I had finally just finished my first 6-inch scope there. And then year after year, there's not quite enough space in the car. I'll bring the telescope next year. And finally, I realized that it had been more years since I built the scope than since I had been alive. And so I figured I really need to get the scope up there and actually observe with it on the hill. And I entered it in the optical competition last year and was super honored to tie for first place. Now, a tie might seem like, so close, but it was actually amazing. The other person who was there had a beautiful scope. We were observing all night, had some great conversations, and so I wouldn't have changed it any other way. So at the same time, I was getting really involved at my local observatory, the New Jersey Astronomical Association, the NJAA, and this is where I first started to get my very first taste of research. So there's a very active group there in astrophotography and research and just general observing. We have a 26-inch telescope as well as a myriad of smaller instruments, and this is where I first started getting into imaging. And so in the upper right here are some images that we took many years ago with a 12-inch scope of Jupiter and of Mars, and they're probably not gonna, make it to the front page of Nat Geo, but they were our images. And so you can see the banding on Jupiter, you can see the great red spot, you can see some of the darker features on Mars, you can actually see the polar cap. And so we took these images and we submitted them to the Association of Lunar and Planetary Observers, or ALPO. And so these images are actually really critical over time for folks that are interested in doing planetary research. If you want to understand how the bands across Jupiter have changed over time, if you want to understand how the size and orientation of the red spot has changed, if you want to look at when and how frequently Mars has dust storms, how the size of its ice caps change over seasons, you need these types of images. And so these types of contributions from amateurs are absolutely vital to doing this type of research. So with this, I decided to go kind of dive in and pursue a career in astronomy. So I did my undergraduate at the College of New Jersey, where I studied physics and astronomy. And there I got a real taste of research using the Kepler Space Telescope. So who has heard of the Kepler Space Telescope? Lots of people, right? Kepler was a mission designed to look for exoplanets. It was designed to look for planets around other stars. And so what Kepler did is it basically stared at one patch of the sky right about the size of the tip of your thumb for 4 years. And in that time, it discovered evidence of thousands upon thousands of exoplanets. However, while it's looking for those exoplanets, it's monitoring the brightness of basically everything in the field, so you can use it for a lot of other science. In our case, we used it to look at active galaxies. So these are galaxies that vary in brightness over time. So what you're looking at is the brightness of the galaxy over the course of a couple of months. And what you see is the galaxy is kind of just hanging along, not doing anything too crazy, and then it starts to vary rapidly on the course of several days. And with Kepler data, this is the first time that we could really look at an object with no interruptions. We had a data point every 30 minutes for basically 4 years. And so you could really nail down what's happening as the supermassive black hole at the center of a galaxy is eating and growing and emitting an immense amount of radiation all across the electromagnetic spectrum. I had the privilege to present some of this work at some conferences, and the careful observer there will notice ST member Doug Arian in this photo had come by to look at my poster. But we can never keep things strictly just to business, so if you look carefully, you'll actually see a new focuser that Doug was working on at the time. He brought it over, and we spent just about as much time looking at this really incredible focuser design that he had at the time. But I really enjoyed this process. I enjoyed getting to do the research, to present it with people, to talk with people, and to be at the intersection between research and amateur telescope making. So if you're a student, or there's a student that you know that is interested in doing research, there's a lot of different opportunities depending on where you're at. So your first stop shop is the American Astronomical Society, the AAS. This is essentially the largest astronomy organization in the United States, and they have a webpage with an immense amount of resources. They host national conferences, but the key part is they have a very nice career section of their webpage, which has lots and lots of internships, career resources, and as just a few examples of these, for example, the NASA internship program. NASA hosts its own internship program where they will take students from all over the country, bring them to some national labs, the centers. They can do research with people there, typically over the course of a summer, sometimes longer, and really get their, kind of sink their teeth into research and get that first taste to see if they like the research process. In addition, there's research experience for undergraduates, REUs, which are hosted by the National Science Foundation. And so these are basically research experiences at individual universities all around the country each summer, where students can come, work with someone. They could be doing observational astronomy, taking imaging. They could be working with existing data. They could be doing software development. There's a huge array of projects, but it really gives you time to sink in, focus in, and work on a project in a really dedicated, focused way for a few weeks, few months, and understand if you enjoy that research process. And it really kind of helps give you momentum from that point forward. And of course, I can't not mention our own program at Space Telescope, the Space Astronomy Summer Program, or SASP. And so this is a program that brings in usually 1 to 2 dozen students each summer to work with astronomers at Space Telescope. And again, working on topics from galaxy evolution to exoplanets to variable stars to instrumentation to coding development. And these are all opportunities that can be available basically from high school to post-bachelor students. So a few things that I wish I maybe knew a little bit earlier. The first one, which I got involved early with my local astronomy club and telescope making groups. And I cannot tell you how pivotal that was in my ultimate decision to pursue a career in astronomy. The people that I met, including the people here at Stellafane, is just such a wonderful community. You have people with a wide array of backgrounds, people who are here for the first time and have never looked through a telescope, all the way to the people who have, done things with space missions, everything in between. We have engineers, we have scientists, we have people who just love astronomy, and that network just really, really catapults you forward. In addition, interestingly, you would think, okay, if you want to pursue a career in astronomy, then at undergrad, you should probably go and get a bachelor degree in astronomy. And you can do that. However, interestingly, which I didn't really know until right I was about to jump in, most students will actually pursue a bachelor in physics and focus on astronomy along the way. And that's for a couple reasons. There's many more bachelor programs in physics as compared to a dedicated astronomy bachelor. And in addition, a lot of the courses you're taking early on have a lot of overlap with the other physical sciences. And so it gives you a very wide breadth of knowledge that you can apply to, basically any path that you're interested in doing forward. So a lot of times people do physics with astronomy. In addition, you would think that, going for a career in astronomy basically just requires a lot of math and science. And that is true to some extent, but it really requires a little bit of everything. It requires a lot of reading and writing to read papers and understand new results that are coming out, to write proposals and write papers to share your results, and of course, math and science. And I think the really key point that I want to stress is it's okay not to be good at all of these things. I was not particularly good at math, but the key is whenever you're working on something, you're just not good at it yet. You continue growing, you continue learning, and you continue building. So if I did it all again, I would follow a very similar path, except I would actually probably double major in computer science, which is one of the most surprising things to me. 90% of my work during the day is on a computer. I'm, writing code to take observations or to download observations or to calibrate new data sets, or writing software so that the community can work with those data products. So it's a lot of computer science that goes into the astronomy that we have. So that takes us all the way up through basically the bachelor level. Then I decided to go to graduate school, which was something like this. So just a joke, but graduate school was a wonderful time, also a very difficult time. So this is at the Apache Point Observatory with a 3.5-meter telescope. At the time, they had the mirror cover closed. They won't let you take a picture in front of it without it closed, which is probably a safe idea. And in the lower right, they're standing in front of one of the instruments that we use to actually gather our observations, in this case, gathering spectra of nearby galaxies. So for my PhD work, I focused on the interaction of supermassive black holes and the galaxies that they live in. So supermassive black holes are these very massive, very dense objects that have such an immense gravitational pull that even light itself cannot escape. And for the most part, when we look at the center of most massive galaxies, we find evidence of a supermassive black hole. So as supermassive black hole is eating gas and dust and stars from its galaxy, that material is getting squished down, it's getting compressed, getting heated up, and it's emitting an immense amount of radiation all across the electromagnetic spectrum. And all that energy, all that radiation has to go somewhere. It doesn't just disappear, it goes into the galaxy. And so this is a really, really nice ground-based image. You can see in the center kind of the older nucleus of more yellowish stars, the older population. You can see this bright kind of bluish-purple ring, which are these much younger, high-mass, hot stars embedded in these H2 regions that are just glowing. And if we zoom in with the power of the Hubble Space Telescope, then we can start to get a really, really sharp view. Now, thank you, there we go. Now you can start to look at individual little star-forming regions. You can start to see these dark brown spiral dust lanes as they wrap into the nucleus. You can really start to dissect the structure that's there. So for my research, I was using a lot of Hubble observations, imaging, and spectroscopy. And so if we zoom in one more time, we end up with this really incredible image of a supermassive black hole interacting with its galaxy. Now, hidden somewhere all the way down in the center in a single pixel of this image is that supermassive black hole, all the material it's eating, the entire region where it's emitting all of this light from. And as that light travels out into the galaxy, it interacts with the gas and dust in the galaxy, basically excites it and causes it to glow just like a neon sign. If you've seen a neon sign, you pump electricity through a gas, it makes it glow. Similar idea here, except we're pumping radiation. We're pumping light through gas and we're making it glow and excite like a neon sign. And what actually happens is there's so much pressure from this light that it's actually blowing the gas away from the supermassive black hole. So the question I wanted to tackle is, well, just how much material is being blown away? And so we can figure out about how much material is falling in, and then we can try to measure how much is coming out. And it turns out that there's actually a lot more material being blown away than what's falling into the black hole. So it's kind of this self-regulating process. As the black hole is trying to eat gas and dust and stars, it's actually clearing out the reservoir of material that it's trying to eat. And so this could be very important for how the way galaxies evolve on long timescales. I want to highlight one last thing here. The credit is to Judy Schmidt. So we gather these observations, we analyze them to do our science, but I really wanted some wonderful images to highlight exactly what we were studying. This is not an artist representation. This is real Hubble imaging with lots of filters combined to make a color composite. And this was all done for me by Judy Schmidt, who's an amateur astronomer. So I reached out to Judy. I'd seen some of her wonderful images on Astronomy Picture of the Day. I said, hey, I'm working on my PhD. I really want some images to show people what it is we're studying. I figured I'd never get a response, and about 10 minutes later, I got all these amazing images that just absolutely knocked my socks off. So it's really a wonderful way to connect the detailed science we do with actually showing you what you're looking at. And what you're looking at is hot, excited gas being blown away from a supermassive black hole at tens of thousands of miles per hour. So that's what I did for my PhD. If you may continue on the career journey into astronomy or interested in graduate school, a few things. So the first thing that I always love to throw out there is, how much do you think it costs to get a PhD in astronomy? So let's start. How many people think it's $50,000? We're going to keep going up. $100,000. Got a couple buyers, okay. $150,000. Got another couple, $200,000. We got it right? The answer is 0. Wonderful. That is one of the first times I've heard a whole crowd in Houston say 0. I love that. The answer is graduate school in astronomy is free. Now, of course, there's a little asterisk there. In a lot of areas of physical science, you don't necessarily get to go to school for free. The asterisk, of course, is there has to be some way to earn your keep. So you can do this either by being a teaching assistant and teaching labs or courses, grading coursework, or you can be a research assistant where someone's essentially buying back your research time with their grant money. So that way you can focus on your PhD, you can focus on your studies, while you earn a small stipend that is just enough to pay your rent. So it really is one of the best deals out there in terms of education. However, it is worth noting that it is quite difficult and demanding. And so it's always important to ask whether or not it's something that you need. And so this is the last point I want to highlight here, is that there are many, many different jobs in astronomy. So you could, for example, you could be an observatory technician, you could work and build instrumentation, you could work in public policy and space law, you could work in public outreach, you could be at a national lab, you could be a professor, you could be a software engineer, you could be a data scientist. All of these jobs intersect at astronomy. And so depending on your interests and what it is that you want to pursue, there's a lot of really great paths out there in astronomy, some of which do require graduate school and some of which don't. So that takes us to the present day, where I'm now at the Space Telescope Science Institute in Baltimore, Maryland. And as you might have guessed from the name, one of the things we're best known for is running space telescopes. So we operate the Hubble Space Telescope and the James Webb Space Telescope. And these are two of basically the powerhouses in astronomy. Hubble has been in orbit around the Earth for nearly 35 years, has a mirror that's almost 2.5 meters across, and it's revolutionized almost every aspect of astronomy over the course of the last 3 decades. More recently, we have the James Webb Space Telescope, or JWST, and that telescope has a mirror which is 6.5 meters across, which means it would probably just about fit between these chairs up here. It is absolutely massive to think. That is just the mirror. The actual sun shield, its entire instrument bay, that spans about the course of a tennis court. So these two telescopes have really revolutionized what we've done through astronomy. However, I've also had the opportunity to use some ground-based telescopes. So who recognizes this telescope? If you know the name, shout it out. Palomar, yes. So this is the 200-inch Hale telescope at Palomar Observatory. And so this was one of the largest telescopes in the world for a very long time. And if you don't recognize the picture of it, you might recognize one of the chalk drawings. So I grew up watching a documentary about how the 200-inch was made, and I thought it was so cool. And then when I actually got to go there as an astronomer and use it, that was crazy. And looking at some of the diagrams, I noticed the little initials in the corner, R.W. Porter. Russell Porter created some of the most realistic charcoal drawings of the 200-inch, a lot of which were actually really used in the construction. Initially, they weren't really meant to be necessarily technical diagrams, as I understand it, but he made these beautiful cutaway diagrams showing different orientations, different aspects of the telescope, and they were so incredibly detailed and realistic that they could really be used to understand how the telescope was put together and would operate. Just another example of how an amateur astronomer made a massive contribution to astronomy. So now I want to transition into the role of professional-amateur collaboration. Before I do, I probably only filled maybe half the time total today. I want to make sure there's plenty of time for questions. So if you have a burning question on anything we've talked about so far, I'd be happy to field it. Good question. So the question was, does Space Telescope operate any other telescopes as well? So the Hubble Space Telescope and the James Webb Space Telescope are the two currently active missions. The next one, which is coming up in just about a year or two, is going to be the Roman Space Telescope. And so Roman is already being built, its mirror is done, its overall structure is complete, and the idea is to basically be a super Hubble in the sense that it has the same aperture as Hubble, 2.4 meters, but its camera has 100 times the field of view. So where you would have to take Hubble and point it 100 times to get a large mosaic of the sky, Roman will be able to do in one shot. So it's going to be an incredible survey instrument. You're going to be able to do huge statistics on galaxies, on stars in the galaxy, and all of the data will be public, as I'll talk about. So that's the next one coming up. And I'll talk a little bit more about the data that we host as well. That it was what? I'm sorry? That it was a what? I'm sorry. That it was a U.S. patent. Interesting. Okay, so I do vaguely recall reading something similar. I can't confirm it, but yes, the comment was that essentially he had the patent for this horseshoe type of design because it was new at the time and ultimately made its way into the telescope. Thank you. I appreciate that. So that's how he got hired. Good to know. Any other questions on careers in astronomy?
Your institute, is there anything there open to the public? I mean, exhibits or anything like that, or it's just where you work?
Certainly. So the question was, what is actually at Space Telescope to see? So the Physical Mission Operations Center is off limits to the public. It is possible to arrange tours. You can enter the main building. We have a really wonderful entryway which has a quad screen display running through huge Hubble mosaics along with a 1/5 scale model of Hubble that is basically flying in the entryway. And a lot of, all of our events such as the colloquia, the science talks and things like that are all streamed online so everyone is able to view those. But in terms of the physical building, it is a little bit more limited than some of the other facilities in terms of what you can go and physically see. Sure. Okay, let me take this in two pieces. So the first one was about the resources that I put up. So at the very end, the last slide, I'll have a QR code that you can scan, and it'll take you to a Google Doc with links to every single resource that I'll show through the entire presentation. If you don't have enough service to get it, then I can go ahead and give you, I have cards up here in my email, so you can get all that information. And the second one, if I followed it, was essentially asking if tips for what to do when you have a bachelor's degree in, say, computer science a few years out, is that? Sure. Sure. So we should definitely talk more after, but I think the brief gist is, if you have a background in computer science and you're really interested in general relativity, say, there's a lot of really wonderful work being done in numerical relativity. So developing codes and hydrodynamic simulations that can simulate very extreme gravitational environments. One of the biggest ones of those right now would, of course, be gravitational wave astronomy, where there's just huge volumes of data searching for these very specific types of signals, which requires a lot of coding, a lot of statistics, and a lot of knowledge of relativity. And so a lot of that data is being made public. There are some more opportunities to link in and get involved with that, so let's definitely chat more after.
Sort of two questions. One is, when you're looking at the active galactic nuclei, if you looked at how much energy is coming out, what wavelengths are you looking at? Primarily optical?
Wonderful question. So when we're looking at this hot gas that's being blown away from supermassive black holes, what wavelengths are we looking at? So the images and the spectra that we used were primarily ultraviolet, optical, and near infrared. So basically everything that we can see with our eyes, and then a little bit more red. But it's a good point that only paints part of the picture, because a lot of this gas that's being blown out is also in other gas phases. The two most key ones are in the X-rays, which you need an X-ray observatory in order to study that gas. It tends to be extremely hot, extremely diffuse, but it can also carry a lot of energy with it. And so that can actually dominate the energy budget in some cases. The other side of that is at the very cold end in molecular gas and atomic gas. And so molecular outflow is basically the coolest gas, when stars are trying to form in these H2 regions, they have an immense amount of material there. And so even if you don't get it moving very fast, it carries a lot of momentum with it. And so in order to really build the full picture, you need to go very multi-wavelength, and that's one of the main areas of focus right now in AGN astronomy.
So the second question is, you mentioned you're spending a lot of time programming computers. What language do you typically use?
Yeah, so this is going to be a bit of a sweeping statement for online recordings, but I'd say most of astronomy is moving to Python. So for years, a lot of astronomers use the interactive data language, IDL, but that requires a license and it's not freely accessible. So a huge part of astronomy is shifted to Python. At Space Telescope, all of our user tools, the new Jupyter notebooks, things we develop, a lot of that is all in Python because it's open source. And because it's freely available, anyone can develop it. And as a part of that, there's kind of a whole nother ecosystem known as AstroPy, so AstroPython. And so this is a community-led effort to basically take lots of very useful tools from other languages and develop new tools and put them into Python in a way that they can interact nicely together. And so this is, if you're interested in computer science and software engineering, AstroPy is a completely open source, community-led effort. They have a core team, and they also have what they call affiliated packages, so you can basically develop something yourself that kind of plugs in. And that is an absolutely wonderful way to get involved because those tools are needed so very much. Let's take one or two more, and then we'll take the rest at the end.
I'm not the astronomer and telescope maker he is, but I have a very basic question.
Please.
I assume that the universe is continually changing, and you're collecting data. This data that you collect, are you sharing it with other institutes?
Absolutely. So the question is that things are constantly changing. All this data that we're sharing, are we sharing it with other institutes? So it's a little bit of a spoiler for later. All of the NASA-led missions, those are funded by your tax dollars. And so all of that data is completely publicly available. And I'll show a little bit later how you can actually go and access that data for anything that you would like to use it for. Let's take one more and then we'll keep going.
When you say near infrared, for any of these telescopes, what wavelengths are you talking about?
Sure.
I've worked in the area, and they got more names for more wavelengths.
Yeah, this is one of those great things in astronomy where you name things and then as you learn more, things change, right? That's why our star classifications are O, B, A, F, so on, right? They're not in alphabetical order. So when we say near infrared, or infrared. So Hubble goes out into the near infrared. It reaches about 1.6 microns, or 1,600 nanometers, 16,000 angstroms. And James Webb basically overlaps with that. So it starts around 600 nanometers, so just shy, just blueward of H alpha, for example. And its longest instrument goes out to about 25 microns into kind of the mid-infrared in those wavelengths. Okay, great. Wonderful questions. I really appreciate it. If you have more, we'll definitely take them at the end. I do want to make sure that we have plenty of time to focus on the value of professional amateur research. And so one of the things I always like to point out is that there's very little difference between, quote unquote, professional and amateur. Amateur is a misnomer in many ways. Really, the only difference is whether or not you're getting paid to do it. And so professionals get paid to pay the bills, and amateurs get paid to feed the soul. That's the way I like to think of it. And so it is true that professional astronomers can have access to, larger observatories, more resources, but that's only if they can get the time or if the facility they're at has access to those instruments. So for example, if you want to get time on the Hubble Space Telescope, which anyone can apply for, you write a proposal, you submit it, it's reviewed by experts, and then they basically rank them and they draw a line and say, this is how much time we actually have available. That ratio is about 7 to 1, which means you have a 1 in 7 shot of getting time on Hubble each year. If you don't get it, you can try again next year. If you take that to James Webb, which is allowing all these new incredible discoveries, that number is roughly 10 to 1. So if you want time on the James Webb Space Telescope, you put in proposals, you have about a 1 in 10 shot of actually getting that data. So, in a lot of ways, a hobby can both be more rewarding than a career in certain aspects because you can pursue what you want, and amateurs have dedicated time and resources and skill sets that we cannot necessarily do. If you have a small observatory with a camera in your backyard, you can go point it at anything you want at any time. If you want to just scan the sky and look for exploding stars, you can do it. If you want to monitor long period variable stars that take 800 days to vary, you can do it. No one's there to say, okay, no, you have to, justify this in certain ways. So that is a really key strength that the amateur community has. And so there's a number of opportunities. I'm going to highlight basically 4 key ways and talk through them in just a little bit more detail. So the first one is to join a pro-am research collaboration. These are structured organizations where professionals and amateurs get in contact and say, hey, here's the science that we're working on. This is what we could use from you. If you can help, join us. A second way is to do research at your own local observatory, or start an observatory, or start a research group at your observatory. You can lead any type of program that you're interested in. A third option is to analyze data that already exists, and I'll highlight in particular those from the NASA Space Telescopes because all of that data is publicly available. Some data is proprietary for 1 year, but after that, it is completely publicly available to anyone on the globe. You can download that data and make beautiful images. You can conduct detailed scientific analyses. You can do whatever you would like with those observations. And finally, the last way is to participate in a variety of citizen science projects or develop software, as we talked about. So I want to walk through these 4 in just a little bit more detail to give you some resources. So the first one is the International Astronomical Union, or the IAU. This is one of the largest international astronomy groups in the world, and they have specifically a professional amateur working group that maintains a list of projects. So these are astronomers from around the world that say, hey, this is the science we're doing, this is what we need. And this can involve a wide array. It could say, hey, we're looking for supernovae as they go off. We're going to have something that tells us when it goes off. We need you to point your telescope there as quickly as you possibly can because we can't get the big telescope there as fast as you can, and we want to see what's going on at that earliest moment. It can involve analyzing data that's already there. If you're looking for minor planets, things coming by Earth, you're looking for changes in images, the human eye is still one of the most powerful tools for doing that, and when you have thousands upon thousands or hundreds of thousands of images, you need a large team of people to do that. So there's a huge list of different types of projects here. You can get involved individually, you can get involved as your local observatory, lots of different types of projects here. One of the biggest organizations that we're going to hear about is the AAVSO, the American Association of Variable Star Observers, and we have 3 talks by experts on that later today, so I encourage you to see those talks. They're going to dig in nitty-gritty about how you can get involved with that, the type of science you can do, and how you can connect with them. But I just wanted to make sure to highlight that so you can stick around for their talks later on. And if you need more convincing of the ways that you can get involved, another example is the Sky and Telescope Pro-Am webpage. So this is a webpage that curates all the articles that they've run over some period of time, basically highlighting the key contributions that amateur astronomers have made into astronomy research. And there are literally hundreds of articles detailing different types of ways that amateurs have made discoveries that otherwise would have been missed or otherwise would have been interpreted entirely differently. So that was the first thing that I highlighted. The second one is basically striking it out on your own. So this could be getting involved with your local observatory and joining or starting a research group. And there are a lot of resources out there to kind of give you a little bit of a starting point. A great point is the Cloudy Nights forum. How many people go on Cloudy Nights? Right? Cloudy Nights has everything. There's wonderful people there with a lot of experience and great discussions. And in particular, they have a scientific amateur astronomy section. And there's great, I was making this talk, I got lost there for like 2 hours. It was so cool. And so there's a lot of great discussion there about, building roll-off roof observatories, what type of cameras they use, how to calibrate your data, how to prepare those results for submission, for publication, so that way they can be seen by the community. Every type of question that you could imagine you can ask here or you can find there. So this is just one example of a great resource. And just to kind of highlight the level of what that can be done, one example is someone that I know personally is Kevin Alton. He's an amateur astronomer in New Jersey. He started his own Under Oak Observatory because it's literally under a giant oak tree, as well as a robotic observatory in Arizona. And what he's done, for example, is take brightness measurements of nearby stars, in this case an interacting binary system, and then he has actually created computer models to show what that looks like. So in this case, we have two stars that are orbiting each other. They partially eclipse, so the light brightness is changing over time. And he's created a model to basically show how they're interacting, how much gas they're sharing, how quickly they're orbiting each other, what the relative sizes are, what their relative mass ratio is, what the relative colors are, all sorts of incredible things you can do with a relatively small aperture scope with a camera. The second layer to this is spectroscopy. Imaging and photometry, measuring the brightnesses of things, that's our fundamental tool in astronomy. The second one is spectroscopy. And so this is taking light, spreading it out as a function of wavelength, and seeing what we see. So this is an example of a spectrum of a planetary nebula, one of the famous ones you've probably looked at recently, and it goes from the blue end to the red end, and you see these individual spikes. These are emission lines from hot gas that's being excited within that planetary nebula. And each emission line tells you something. They come from hydrogen, they come from oxygen, it comes from argon. Each emission line can tell you about the density of the material, how hot it is. It can tell you if there's dust there. It can tell you the elemental abundances, how much you have of each heavy element. And so these types of information are critical for basically constraining models of stellar evolution. And so these are the types of things that you can do with these types of equipment. Now, it's fair to say that that requires a fair amount of equipment, so there are also other options. The third one that I noted was looking at existing space telescope data or other data archives. And so, for example, NASA had a great observatory program with 4 key observatories. We had the Spitzer Space Telescope looking in the infrared, which was operating until just a few years ago. We have the Hubble Space Telescope, which is still flying and delivering these incredible images. Now we have the Chandra X-ray Observatory looking at the most high energy, very excited phases of gas, and the Compton Gamma Ray Observatory, which is basically probing these absolute highest energetic results in the universe, such as exploding stars, things like that. So all of the data from these missions is completely publicly available. A lot of them are hosted at Space Telescope on the Mikulski Archive for Space Telescopes, or MAST. And so this is an example of a search forum. Does anyone recognize that object on the right? Shout it out. Dumbbell, M27. So this is a beautiful object. A lot of us looked at it last night, and it's also been observed by Hubble. And so you can go and download these images in different filters. You can create color composites. You can analyze it in any way that you would like to play with it. All of that data is publicly available, and there are tools there to show you how to access it. So finally, the last thing that requires virtually no equipment other than a computer is citizen science projects. And so one of the best known examples of these is Zooniverse, which hosts a wide array of projects, not only in astronomy, but across the physical sciences. And these are basically, you can kind of think of this as a little bit similar to the IIU approach, where you have specific projects that connect professional amateur astronomers. And so this is just one little screenshot. I think this is like page 1 of 9 of some of the projects that are available. So if you're interested in nearby asteroids, if you're interested in lensed galaxies, if you're interested in searching radio signatures for signs of intelligent life, if you're interested in looking at exoplanet signatures, there's probably a project for you. And the key is a lot of these projects involve image classification or signal classification. And so if you can sign up, make an account, and start classifying images, one example is galaxy disks. So you look at a bunch of images and you say, okay, is this a spiral galaxy? Is this an elliptical galaxy? Are they interacting? Is there a star in front of it? Is there something going on? And you classify that image and provide it with a variety of characteristics. Now, let's say that one person classifies a few thousand images, and then a few thousand people classify a few thousand images. How big of an impact is that? The answer is huge. And the reason is because you have taught a computer what a galaxy is. When you go on a website and it says click the boxes with all of the street lights, the computer has no idea what a street light is. You are teaching it what a street light is. When you go to a website and it says type in this sentence from this newspaper, you are teaching it how to read that sentence. And so by going through and classifying large quantities of images, then astronomers, both professional and amateur, can use machine learning techniques to say, okay, I have all these images, here are their properties. Go ahead now and look at millions of images and tell me something about those galaxies. And now all of a sudden you're looking at studies that are basically as big as the universe. So, my hope today is that I have convinced you that whether you try to pursue astronomy as a career, whether you pursue it as a hobby, whether you pursue it with a huge observatory and a lot of equipment, or nothing more than your laptop, you can do really impactful research. And with that, I'd be happy to take any questions. So kind of, if the question is kind of minimum requirements for doing meaningful, so there's going to be a great talk just a little bit later about the new generation of small smart telescopes, which are incredibly small. You can't see it's hiding right down here by Peter. And so the instruments are getting smaller and smaller, but maintaining their power. And so, of course, it always depends on what you want to do. But if you want to do, for example, variable star observations or look at some of the larger exoplanets, you can get away with a very small aperture telescope, less than 6 inches with a high quality camera. There's a great article in Sky and Telescope about how to basically jerry-rig a DSLR camera onto a tracking mount and do exoplanet light curves for some of the brightest stars. So, of course, the further you want to push it, the more equipment you need, but you can get away with a surprisingly small amount. Sure, yeah. So the question was, we see the fun slide about grad school. So what I will say is that graduate school in astronomy was probably one of the most rewarding times in my life because I was able to really pursue research 100% of the time. I was given the time and flexibility to explore and learn things. But I will also say it was probably the most emotionally demanding experience of my entire life. So there's a flip side to all of those things. This is just a kind of a little funny compilation that I found that I thought kind of touches on some of those points. So thank you. What kind of specializations are there within scientific instrumentation? A lot, I guess. So I think if you narrow it down to kind of the instruments we think of a lot of times, which are usually cameras or spectrographs or some type of sensing instrument that is connected to a telescope, that's going to involve, of course, mechanical engineering to physically build the design, electrical engineering because these have very sensitive electronics, very sensitive photovoltaic systems, and also, lost my train of Optics, thank you, there we go, that was the third one. Optics, because these instruments have incredible optical systems which are getting increasingly more complex. So that's a very sweeping statement, because if you're working on solar astronomy versus deep sky observations versus gravitational waves versus whatever, it's going to vary quite a bit. But I think between mechanical, electrical, and optics, that covers a huge amount of kind of the span. But let's definitely talk a little bit after, a little bit more specifically. I'm sorry? Sure. Oh, yes, thank you. There you go. Yes, so that QR code will take you to a Google Doc that has links to every single resource that I've shown today. If you can't get to it, just grab my card with my email up front, and I'll be more than happy to email it and make sure that you get your hands on those resources. Thank you, I appreciate that. All right, good. Okay. Few more minutes? All right, we have time for another question or two, and otherwise we can meet afterwards, yeah.
So, Mitchell, it seems like you're into studying AGNs. About a year ago, a large research team from China published a paper on NSV 6690, where they believe there's two close black holes that they predicted were going to merge within a year or two. Do you know, is there anything further on that? I haven't been able to find anything.
So the question is, there's a lot of very interesting dual AGN, basically black holes, galaxies that are merging where their black holes themselves are very close to merging. I don't recall that specific system by its name, but what I will say is we're finding more and more of those. They tend to be pretty rare, and the difficulty is with imaging and spectra, there's a lot of other things that can produce those types of signatures, but now that we're getting, particularly with Webb, where you can basically look through a lot of the dust because you're further in the infrared, or using the X-ray missions to look for basically two X-ray sources, we are finding more and more of these dual AGN that are kind of these late state mergers. Good. All right. Well, thank you again so much for giving me the time, and please feel free to meet with me after. Please come up and take a poster as well. Thank you.